Okay, hi everyone. I'm going to be recording on knot theory. And okay, so let's first introduce what a knot is. So a knot is defined as a closed, non-self intersecting curve that's embedded in 3 dimensions and cannot be untangled. And we're going to be discussing a few historical information followed by isotopy, links, and we're even going to see a few applications on this. So throughout the presentation, I do want you to keep in mind, how can we tell if 2 knots are similar or different? So that's something that you should keep in mind as we move towards the presentation. And here we have 2 knots. Okay, so some just background information. A knot has to be a continuous loop and not. So let's give credit to a few mathematicians that are responsible for knot theory as it is today. So the first one is Carl Friedrich Gauss. He developed the Gauss linking integral, which was necessary for computing the linking number of 2 knots. And next we have mathematician, and he is also a physicist, Lord Kelvin. His name is William Thomson. He was responsible for stating atoms consisting of knots, and he explored different knots afterwards. Next, we have Peter Guthrie Tite. He also contributed to the knot theory early on, and we're going to take a look at one of his main things on the next slide. And finally, we have Thomas James Clerk Maxwell. All right, so let's talk a little bit about Peter Guthrie Tite. He had knot diagrams similar to the one that we see over here, so similar to this. These are some of his works that he worked with, and you're gonna notice like his he's coloring the background, so he worked with 2 different colors. He thought this was helpful for distinguishing regions. So the gray area that you're taking a look at over here, all this gray area represents the infinite region, whereas the white one doesn't. And this brings us to the unknot. This is the most basic knot that there is, and it's also known as a trivial knot. And here we have it. Okay, so let's talk about curves in case we haven't seen curves. So the one over here, this is known as a simple closed curve. The second one, this is a closed curve. If you look closely, it's completely closed. And the one that we're taking a look at on the right, this is known as a curve that is not closed. As you see over here, this is an opening. Okay, so this brings us to deformation. The image on the right shows a knot being deformed, but if you look closely, so this is the starting one, and we're moving here, so it looks like it's going through a few moves. So we do not cut knots, we just move things around, and so this is the end result. And as you can see, the knot is still the same, the crossings are still there, it's just been changed as far as appearance. Okay, so this brings us to the connected sum of knots, which is another important piece of knot theory. On the left side, we're taking a look at a schematic connected sum, and on the right side, we're looking at a connected sum of 2 unknots. And remember, we had talked about what unknots were. Okay, so continuation of connected sum of knots. Here we see the first one we're going to take a look at is a curve with a triple point. We look closely, here they are connecting at a point, and the next one is going to show us a curve that has a tangent line. If you look closely, this is a tangent line right there. Okay, this brings us into virtual links. So virtual link diagrams are a collection of n closed curves, and we have 2 kinds. So we have a classical crossing and a virtual crossing when it comes to virtual links. Okay, so this is going to bring us to the Riemann-Meister theorem. So these moves change the projection of knots, and the crossing relationships might change, but the knot remains the same. So as long as we're using all 3 moves from this theorem, 2 knots can be claimed to be equivalent. And we're going to take a look at these 3 rules. So the first one is we can take out and place a twist. Here's an example of this. And the second one is we can add 2 crossings or we can remove 2 crossings. So here, as you can see, we're adding them in. And then the third one is we can slide a strand from the knot from one side to the other. Okay. And here we see it again. This is the first one, followed by the second one and the third one. So these 3 moves could be used and the 2 knots will remain the same. They will remain equivalent. And this brings us into our next one. So links, disjoint knot put together. So a linking number, the Riding Meister moves do not affect the linking number whatsoever. Okay, so let's talk about isotopy, which is another important feature of knot theory. So there's 2 kinds. There's planar and ambient. So let's first talk about planar. So here what we're taking a look at is we're taking a look at 2. This is one and this is the other one. And what we're seeing is that they are equivalent through a finite sequence of planar isotopy moves. And keep in mind, planar isotopy, the stretching is not going to affect the diagram because if you look closely, it's not interacting with the crossing. So nothing is happening to the crossings when we're using planar isotopy. And ambient isotopy is a little bit different. It's when we're using the Riding Meister moves and there exists equivalences between the knots or links, and this is an example of it. If you can look closely, you'll see that there's the 3 type of movements happening here. And here we have the first one, the third one, and so on. Okay, so this brings us to tricoloring, which is one of my favorite features of knot theory because it's colorful mainly. So tricoloring is used to represent the undercrossing where it starts and ends. At each crossing, 3 colors appear. As you can see over here, this is 3 different colors appearing, 3 different colors appearing, and 3 different colors appear. So always at every crossing, 3 colors appear. And a knot is considered to be not tricolorable if this is not the case. So let's take a look at which ones work. Okay, so here we can see that this seems to have 3 different colors at every crossing. Over here, you're going to see that that's not the case over here, and that's not the case over here either. So this does not work for tricoloring. And let's take a look at another one. Same thing over here. You're going to see that it does not work here either because we don't have 3 colors. Over here, we do have it, but it needs to be for all of them. So if one of the crossings don't have 3 colors, then tricoloring does not work. And the unknot, actually, let's go back for a second. So the unknot, which is just a circle, this actually is also not tricolorable because it's just one thing. Thought that was interesting. Okay, so let's identify which knots are the same and which aren't, as I told you earlier on the presentation to keep that in mind. Okay, so let's take a look at 1 first. Okay, so are these the same? So these are not in color, but this would have been a nice example of a tricolor. And we can see that this right side over here has been moved around. So this is, these are the same. If we're looking closely, this side has been deformed, but it's done in a way that nothing has been broken, it hasn't been cut, and the number of crossings have not changed. So still the same number of crossings. So these 2 knots are the same. Let's take a look at another one. So over here, this one looks a little bit more intense, but we can also see that it's the same number of crossings, so these 2 are also the same. And it's not usually as easy to see, but if you look closely, you can take them. Okay, so this brings us to a few applications. Like, there's a lot of applications for knot theory, from biology, DNA synthesis, statistical physics, quantum computing, and chemical synthesis. We're going to take a look at 2 of them. because of time. So Notepad is one of them. So it's a platform that allows us to draw two-dimensional knots, and we can modify them, because knots are not that simple to modify on paper if we wanted to. So here we see the Writing-Meister theorem once again being used. Notepad system works in a way that each move is remembered and you can easily navigate. So we're moving from here to here and so on and so on. We can this tool actually allows you to go back and see what the last move was and how it affected the knot, which I thought was pretty interesting. And then another application I wanted to share was knots in DNA. So these are coiled knots, which is pretty interesting. There's a book called Applications of Knot Theory, using knot theory to unravel biochemistry mysteries, advances in the mathematical sciences, and I do encourage you to check it out. It's pretty interesting. And this over here specifically is proteins working with DNA. So these are our knots. So basically what we have in this image, it's showing us that the image is changing through topological changes. Is being done through replication. So there's this protein called topoisomerase that is unknotting the DNA so that the cell is being allowed to split, which is pretty cool. And it's uncoiling it. And that's about it. So thank you for watching. If you have any questions, please ask. And these are a couple of my references that I used. Thank you.